All right, so E, this is for Violetta and Jeremy and all this. So E is 1.08. Come on. Great. Oh, okay. All right, F. What effect would each of the following have on the measured cell voltage? Okay, this will likely be a question on the test, and you will have to defend your answer or justify by some means. So what I would recommend, we have that chart that you can memorize, but I think it's easier if you'll think about the hills and the valleys. So when they start asking you, will the voltage go up or down, refer back to your original equation. So what was our equation from part A, I think?
2CR plus 3CU.
Well, which one has a chart on it? Okay, so 2Cu plus 3
Cu plus
2. Okay, goes to.
Yields 3 copper plus 2 chromium plus 3.
Okay. So the first one is, what if you added 20 milliliters of 2 molar copper sulfate to the copper half set? So 2 molar, is that higher or lower? Higher. All right. Now copper sulfate, are we doing that at copper plus 2 or copper solid?
Copper plus
That's solid.
What now?
The solid is solid.
Copper metal, right, would be the solid. Okay. So this is copper sulfate soluble, so we're going to get copper plus 2. And it's going to be higher than normal. So heel. So you go with the heel, this is the heel part. Higher than normal copper. What's normal? 1 molar. Because it says 2 molar is higher than normal. So I'm putting the heel there. Okay, just to represent what's going on. Alright, so I have more copper than I usually do. I'm going to shift to the so I'm going to shift this way. I don't cross the arrow if I go that way. Alright, you got to shift across this arrow. Okay, shift away from heel. You got to use up that extra copper that you have. So I'm going to be using up that copper by going to the right. Okay, if you say going, the arrow has to be across this. So going to the left would look like that. You'd be making more copper and more, and you'd just be building up on that heel. Okay, that's not what we want to do. So we're going to go to the right, using up the excess. And as we do that, our voltage is going to go up. Okay, if you shift right, your voltage goes up every single time. So if you're going to the right, your voltage is going up. If you're shifting to the left, your voltage will be going down. Alright, so for example, if part 1 would have said 20 milliliters of 0.005 molar copper sulfate, that would have been low, right? So we would have had a valley here.
Oh.
So then I would have shifted into the valley, so left. I'm shifting left, so my voltage would go down. Okay, left, down. Because you're going the wrong way, your voltage will go down. If you go to the right, your voltage will go up. Okay. All right, let's look at, this is part 1 again, but do a second example here. Same equation. Chromium plus copper plus 2 goes to copper plus copper. Now when you're doing this, like say you're on a multiple choice and they never ask you to write a balanced equation, but they're asking you which way would it shift. You can just do like a sketch of the equation. Just make sure you flip one. You don't necessarily have to worry about balancing when you're in a hurry and they're asking you this sort of question, because it has nothing to do with the coefficient in front of it. Okay. In this case, we have 20 milliliters of 2 molar chromium nitrate. So that is high or low for what species in my balanced equation? Okay. So heel. causing me to shift left. So I have too much product. So I'm going to get rid of some of it by going left. And as I go left, my voltage goes down. It's kind of, some of you are better biology than others, so if this helps, fine. If not, then forget about it. But it's sort of like osmosis in a sense, like you're going to go away from high concentration, okay, and then you're going to go towards your low concentration.
I don't remember like what the arrow. I'm confused about the arrow. Cause okay, I get the yield.
Okay.
But I don't know like how do you break that.
Okay, you go away from heels. Okay, but you have to cross this arrow.
Oh, you gotta cross the other arrow. Okay.
Yeah. So this is your reaction direction. Okay? So you got to decide, am I going to go the usual way, or am I going to go backwards?
You go usual way, you won't cross it. So.
Yeah. If you go the usual way, voltage goes up. If you go backwards, voltage goes down.
Okay.
But you have to, no matter which way you're going, your arrow has to cross this arrow. Okay? So it can go with it, voltage goes up. It can go away from it, voltage goes down. What, Earl? How do you know it's a valley? So our usual molarity is 1. So if they tell us something happened so our molarity is less than 1, valley. If they tell us something happened so our molarity is more than 1, heal. Okay? How is, we've seen this example before where we made a valley. Y'all remember that example from the free response? Something happened to create a valley. We made a, starts with a P. Precipitate. So if you make a precipitate with something, it's leaving the solution. It's making a solid. Because that would create a valley if you make a precipitate. So for example, I don't know, something that copper creates a precipitate with, I don't know, phosphate. Okay. So if you added some phosphate in there, copper would make a precipitate with that phosphate. So that would make coppers go down. We would shift away from hills, but you shift into the valley. So we would shift left, making our voltage decrease. Okay? Same thing can happen with chromium. You can make a precipitate with some chromium, so we have a valley at the chromium. That would make us shift right into that valley, and then our voltage would go increase. Voltage would increase. Okay? So if you're going right, voltage goes up. Going left, voltage goes down. So you can say that on the test. You can say the voltage will fill in the blank because the reaction shifts right or shifts left. So if it's going up, it's because it's shifting right. And if it's going down, it's shifting left. Now, I don't think we talked too much about temperature, but the effect of temperature on voltage is not necessarily what we would expect. So when the temperature goes up, that doesn't mean the voltage goes up. These are the things that are going to change our voltage. It's shifting our reaction.
But it still won't be standard, so you still wouldn't lose the charge.
Right. All right, questions here?
It won't be standard, so you can use like the half reaction part.
Okay, any questions about, we're going to practice something a little newer, but any questions about things that have been previous to this? Right, the homework is more difficult than the test, okay, but that's a good thing. You have as much time as you need on homework. You have the answers, you have your notebook, you have my phone number, etc. Okay? So I'll be here this afternoon, and I want you to get those done, but just know, like, don't get super stressed out if it takes you 15 minutes to do one of those, because those are difficult. Any immediate questions from the homework?
No, that's something.
Okay. What? Yes, sir. You got 2 right. Three right?
No. Like 5.
5 right. All right, anything else? Yeah, he knows.
So I should have done more and more.
That's true. Okay. Notes for today. Writing electrolysis reaction. All right, think about the Venn diagram. If we're talking about electrolysis, those are the ones that are not spontaneous. Okay? So when you're doing galvanic, think back to the bell ringer, how do you decide how to write your reaction? How do you decide which one flips? The one that's lower on the chart, right? Because if you flip the one that's higher, you'll end up with a negative voltage. But galvanic always has a positive voltage. So here it's the opposite because electrolytic always has a negative voltage. So you're not going to flip the lower one. Most times you'll flip the higher one. Okay, so we'll talk about how to write those reactions. They're a little different. So to start off, we'll add notes to both of these categories. So you can either leave space between them or we can draw arrows down. Okay, we'll do molten first. It's the easiest, and then we'll do aqueous because water could be involved in your reaction.
Is it a lot of notes for each of them?
Maybe like 5 lines. Alright, in a molten solution, that means melted salt. Okay, if you want to make yourself a note. So if you have a molten solution, that just means that whatever's in there has been melted down. Okay, and we think about molten lava. This has got to be really, really hot because salts are difficult to melt. So molten refers to that very high temperature. So you have a melted salt. Okay, in this situation, whatever your cation is from your molten salt will be reduced at the cathode. And whatever your anion is in your molten salt will be oxidized at the anode.
So with these, I know you said you can pick the higher but how would you still, the one that's with the lower value, that's still getting oxidized or still?
Whichever one you flip, which in this case will usually be the higher one, is going to be oxidized. So your anode is still being oxidized, your cathode is still being reduced, your electrons are still going anode to cathode, but you have to make them go because that's not the direction they want to go. They want to go the other way. So for example, in the bell ringer, the electrons were going, help me here, which one was being oxidized? Chromium? So they were going chromium to copper. In electrolysis, we could make them go copper to chromium, but we'd have to supply a battery or something. So it can happen. We can make it go the other way, but we just supply the energy. Okay, on its own, it's going to go chromium to copper. Okay? But copper to chromium, just hook up a battery and it'll do that. Okay, so let's take the example of sodium chloride. If this was molten. Notice that your electrodes are not sodium and chlorine. Okay, they're just some metal that can conduct electricity through. So inert electrons. So these are really the only two things you have. And when you melt that down, you're going to get Na plus and Cl minus. Right? Na plus is a cation or anion? Cation. So it's going to be reacting at your cathode. Okay, so look up on your sheet the reaction for sodium. Your voltage right there.
Negative 2.71.
Okay, what is the reaction? Sodium plus. Okay. Alright, so that's the one, the cathode, the cation one, it does not get flipped. But your anode is the one that does. Okay? So we need to find Cl minus, but we need to find it on the right hand side because it's got to get flipped over. 2Cl minus. Okay.
It's 139.
It's fine now.
1.36.
Did you flip it?
Negative 1.36.
Okay, so you're still changing the anode sign. Notice that chlorine was higher than sodium. Okay, and it was the one that gets flipped in this non-spontaneous reaction. The opposite of what should occur, we're making it happen with a battery. Okay, so overall we got a very negative voltage. We got 4.07, negative 4.07 volts. All right, well, what we can say here is this is how much is required. Okay, so how much is going to be required. So if you have a battery that's less than that, less than negative 4.07, then this will not happen. So notice the picture here. We got sodium going to sodium solid at the cathode, and then chlorine going to chlorine gas at the anode. You see those green bubbles? Okay, chlorine has like a greenish hue. So they can ask you questions like, what would you see at the anode? So at the anode, we would see these bubbles forming. At the cathode should be getting good. Okay. The anode is not going to change its mass though, because we got a gas forming. Okay. So I know we talk about the anode getting lighter, but that's only happening if you got your anode actually reacting. But here, it's just a random piece of metal, and we're making it gas. Electrons still going anode to cathode, and then your voltage required would be 4.07 volts. So if we think back to the bell ringer, what was that voltage? What did we do? Okay, so if we wanted to make it go the other way, we would have to get a battery that was at least 1.08. Alright, questions so far? Alright, to put these together, we won't work through the whole thing, but you do it just like you do on the galvanic. We'll multiply this one by 2, so our electrons can cancel, and then our balance equation will be 2 Na minus plus 2, Na plus 2 Cl minus goes to Cl2 plus 2 Na. Alright, now, this is not in water. What would happen if you made sodium metal in water? It would explode. Okay? So this is not going to happen in water. This is only going to happen in a molten solution. So now let's talk about aqueous, or in water. In water, you're now going to have two choices. So if it's molten, your cation is reacting at your cathode, your anion at your anode. But if it's not molten, then you got water that could be reacting. Okay? So in the aqueous, at the cathode, you'll have your cation or water. Okay, the cation or water. I wrote the reaction there for water, but it's on your chart, located at negative 0.83 volts. So you're going to have to make a choice. My cation or water, which is it going to be? And the way you pick is the one that's higher between the two will be at the cathode. The one that's higher between water and your cation. Okay, at your anode, similarly, you can have your anion, like in the molten, or you could have water being oxidized. Okay, I wrote that reaction as well. I went ahead and flipped it from what is on the paper, okay, because it's at the anode. I did not flip that voltage value yet. Okay, so the voltage for that one is 1.23, so we would flip that. Right here, you're going to make a choice with which one is lower for your anode. So cathode, cation or water, which is higher. Anode, anion or water, which is lower. You may want to turn to your voltage chart and find these two. There's two reactions for water. One occurs at the cathode and one at the anode. And that seems to be the most confusing part. People will use the wrong water in the wrong situation. So on your chart, there's two water reactions. The one that's the high, 1.23, the one that we flip over, that's your anode water. And then the one that you don't have to flip, that one is your cathode water. Yes, sir.
You choose which one's lower after you flip or before?
Notice on this one that I'm calling the anode water, on your chart there, water is a product. So do you see that? Okay. So when you flip it, water would then be the reactant. So that's why that one's the anode. Okay? Because after it's flipped, water's on the correct side, the reactant side. This one's the cathode because before it's flipped, water's on the correct side. If you flip it, water would be a product. We're not making water, we're using water in our reaction. So let's try sodium chloride again. This time it's in water. Like I need to do this right. All right, so we have at our cathode two choices. What are our two choices? Sodium or water. And we're trying to pick which one is high, okay, of the two. So on the chart, which one is higher, sodium plus or H2O? Okay, so we're going to go with the H2O reaction. So at the cathode, we'll have 2 H2O plus 2 electrons goes to H2 plus 2 OH minus. That'll be our cathode reaction. Our voltage there is negative 0.83 volts. All right, so our products at the cathode. What are our products at the cathode? What are we making? hydrogen gas, and hydroxide. What is this, an acid or a base? A base, right? What would an acid be? H plus, right? H plus. So we're making hydrogen gas and a base. So if we drop some of that phenolphthalein right here, what color would it turn? Pink. Good. So they can ask you questions like that. If this was H plus, it wouldn't turn any color. Okay, but we're making a base at the cathode. All right, at the anode, we have two choices. They are what? Cl minus or water. Make sure you're looking at the correct water. We want the lower one.
After you flip it, right?
Nope. Just on the chart, which one's lower? The water is lower. Okay, so we're going to use the water again. We're going to flip it. So it's going to be 2 H2O goes to 4 H plus O2 plus 4 electrons. Now, at the anode, what should we be making? H plus, that's not a gas, and oxygen gas. According to the picture, what are they making at the anode? Chlorine gas. Okay, so this picture, and I'll explain why in a second, but this picture is not correctly reflecting what would happen. We would make oxygen gas. Okay. Have you ever heard of a saltwater swimming pool? Yes. Okay. So the way a saltwater swimming pool works is, you don't have to put all the chemicals in there, and they don't use a filter in the same way that like a regular swimming pool does. So they're a little bit cheaper to operate, but you really have to monitor your salt level. The way it works is they put salt in the water, just like this, and instead of a filter, they have these electrodes. They run the electricity through the water as it comes through this filter. Okay? As the electricity runs, they're making hydrogen gas, and then what they do is they amp up their voltage so high that the chlorine will produce the gas too. So it's called over voltage. Like they put their voltage up higher than it would be required, and then it makes the chlorine gas. So if you use just a regular voltage, you'll get oxygen gas. But if you amp up that voltage, then you'll get chlorine gas, and then the chlorine decontaminates the water. In the same way if you dump chlorine in like you would in normal. And so this is just an example of how that could be used. So cathode and anode for these two. Here are the voltages after we flip it. 1.23 volts. So a total there of negative 2.06. So in a swimming pool, they would turn their voltage to like 6. Okay, so over voltage to get that chlorine gas to form. All right, to put these together, what would we have to do? Okay, so we would multiply which one? The cathode by 2. Okay, and then we could put them together. Okay, question? I think the bell's about to ring, so I don't want to start another one of these. I do not believe that there are any of these on the test tomorrow. Okay, so focus on, make sure you can use the map well. So there's a lot of homework problems like that. Make sure that you can do galvanic, forward and backwards, calculating voltage, writing the equations, all that. Okay, so you should be really familiar with that. What's the purpose of the salt bridge? Where do the electrons go? Those details should be hammered in your brain.
Are we going to be able to use our notebooks?
Can you use your notebooks tomorrow? Probably. Your electrons need it can. Then yes. Yeah, let me get it. Alright, if there's anything you didn't understand about this quiz, ask that, because this is similar to the free response for the test.